Good morning. I welcome you all to the session of fluid mechanics. Last class we started the discussion on principle of similarity, and we have recognized that the physical similarity, complete physical similarity between two problems of same physics but operating under different conditions, to be obtained we have to have three similarity criteria. One is geometrical similarity, kinematic similarity and dynamic similarity. While the geometrical similarities were the similarities of shape, that means the ratios of corresponding dimensions are same. The kinematic similarities are the ratio of corresponding velocities at similar points between the two systems to be the same. The dynamic similarities tell that the ratios of corresponding forces at similar points in the two systems must be same. Then we recognized in general the different forces acting in a fluid flow, or general forces causing the fluid flow. So general forces causing the fluid flow are viscous force, pressure force, surface tension force, gravity force, elastic force, and the vector sum of all these forces give rise to the resultant force, which ultimately causes the fluid to flow. So this is taken in consideration of D'Alembert's principle that inertia force plus all the external forces to be 0. And one by one we discuss the ratio of the two forces governing a flow problem, which represents the similarity, dynamic criteria of dynamic similarity, and this was expressed in terms of dimensionless parameter, because ratio of two forces is dimensionless, and which comes in terms of different parameters. One is known parameters, conventional parameters. One is the geometrical dimensions, another is the flow parameter like velocity and pressure, another is the fluid properties like viscosity and density. And he evaluated for flows governed by viscous and inertia forces, the ratio of viscous to inertia force and pressure forces, of course, ratio of viscous by inertia force or inertia force by viscous force is the well known Reynolds number, rho v L by mu. L is the characteristic length, v is the characteristic velocity, rho the density and mu the viscosity, and known as Reynolds number. Similarly, we derive that the ratio, magnitude ratio of pressure force to inertia force comes out to be delta p by rho v square, where v is the characteristic velocity and known as Euler number. So today we will see such things for flow where the gravity force is dominant, where the gravity force is dominant, where the gravity force is dominant, along with the other force, pressure force for example. So when gravity force is dominant, then definitely the ratio, magnitude ratio of gravity forces to the inertia forces represents a similarity criteria. Then for dynamic similarity, the ratio of gravity to inertia forces to be same for two problems. So how can you represent this? Now if we recall, or you can just tell that the gravity force is proportional to mass into g. Mass is proportional to rho into L cube. L is some characteristic length of the problem. So rho L cube g. Inertia force, as we defined, is proportional to mass into acceleration, and acceleration is proportional to some velocity by time, and time is length by velocity, the way we derived it earlier. And if you recall, it is rho L square v square, where v is any characteristic velocity of the problem, L is the characteristic dimension. So therefore, if we now substitute this equation of proportionality, then the ratio of Fg by Fi, better we should write this as a magnitude ratio, it looks well. So this is proportional to rho L cube g by rho L square v square, and it becomes GL by v square. So therefore we see this dimensionless group, this is obviously dimensionless. If you put the dimensions, you see that this is dimensionless. This represents the ratio of these two forces, magnitude ratio, proportional to this. Magnitude ratio of these two forces is proportional to this. And therefore, in two dynamically similar systems, this has to be constant. For which system? System dominated by gravity force. This happens for flow with a free surface, like flow through open channels. So under two different sets of conditions, this type of problems, for dynamic similarity to be maintained, this has to be maintained constant, this dimensionless term. So a square root of this GL to the power half conventionally, sometimes even this one is known as Froude number, F-R-O-U-D. Froude is the name of a scientist who first discovered it, Froude number. In the study of ships, he was basically a naval architect, GL by V square. This was, sometimes this is referred as Froude number, there is no such hard and fast rule, sometimes the square root of this represents as Froude number. So, maintaining a constancy of this number means the constancy of its square root, does not matter. Now, I consider another cases of fluid flow where surface tension force is dominant. Surface tension force is dominant. Force is dominant. So, this happens in case of flow of free jet or flow of a thin sheet in ambient. Whenever there is a separation or demarcation of two fluid surfaces, that means there is an interface, the surface tension force becomes dominant. So, flow of free jet, flow of a thin sheet, or the flow of liquid through a small capillary tube, vertical flow, small diameter tube, the surface tension force is very important. So, now here also for dynamic similarity, the magnitude ratios of surface tension force to the inertia force have to be made constant for the two systems of the same physics, that means dominated by surface tension force. Now again, what is the surface tension force magnitude? This is proportional to surface tension coefficient sigma into some characteristic length. You know the surface tension coefficient is defined this way, that we have read earlier, that is times the length, characteristic length defines the surface tension force. Fi is proportional to rho L square V square. So, this ratio ultimately, that is again if I write Ft by Fi, the magnitude ratios of these two forces is proportional to sigma L divided by rho L square V square. That means this is equal to sigma by rho V square L. So, this is the dimensionless term which represents the ratio, magnitude ratio of surface tension to inertia force, has to be kept constant in two different systems where surface tension force is dominant. That means in case of free jet flow, in case of flow of liquid sheets, in case of two systems depicting the flow of liquid through very small diameter tube, but under different sets of conditions, but this ratio or this term, combined term, dimensionless term, have to be same, have to be kept same if the dynamic similarity between the two systems are short. Then I come to another type of flow situations where elastic force is important. Of course, this type of flow situation is beyond the scope of this book. This is important or dominant, whatever you tell, dominant. Earlier I wrote dominant, elastic force. In case of compressible flow, when the density of the fluid changes very fast with respect to pressure, this happens when the fluid velocity approaches sonic velocity or crosses the sonic velocity, then the elastic force becomes dominant. Now in that case, the magnitude ratio of elastic force divided by the magnitude ratio of elastic force to the inertia force, that means magnitude of elastic force divided by that of inertia force, is the dynamic similarity criteria. What is this? Very simple. The magnitude ratio of elastic force, as you know, is proportional to coefficient of elasticity, that is bulk modulus of elasticity, times the volume, that means L cube, some characteristic volume, that means cube of the characteristic length. Fi we already know. So therefore, this ratio between the elastic force and the inertia force is proportional to EL cube divided by rho L square V square. So therefore, this becomes is equal to E, what is that? EL cube, sorry, L square, because modulus of elasticity is the force per unit area, I am sorry. So E by rho V square. So this is known as Cauchy number. I am sorry, I could not mention the earlier one, you have written it. The earlier one is known as Weber number. You must know this name. This is named after the German scientist Weber, sigma by rho V square by L, that is the representative magnitude ratio of surface tension to inertia force, Weber number. Similarly, representative magnitude ratios of elastic to inertia forces, which is the dynamic similarity criteria parameter for the flow situations where elastic force is dominant or important, this is known as Cauchy number. He is a mathematician, It's a French mathematician, Cauchy. Now, Cauchy, whatever way you spell, this is a proper noun, Cauchy number. So now this number, this term can be expressed in a little different way. Reciprocal of this and make a square root. Then you get, that means equality of this number E by rho v square means the equality of this number. Doesn't matter because you take reciprocal of this number with a square root, we get this. Now you know the bulk modulus of elasticity in case of gaseous system, we have to specify another constraint for the path for which the pressure and volume changes. So if we make the changes in an isentropic process Es, then this term will come V by root over Es by rho. And exactly for the flow situation where elastic force is important, the flow is so fast, the velocity is so high so that the elastic force becomes important and compressibility comes into consideration. Any change in the density or volume due to pressure is considered very fast, and so that this is considered to be adiabatic. Thermodynamically a fast process means an adiabatic process because there is no time for heat to be transferred, and also within a very small zone the change in density occurs so that it is frictionless, so that it is, we always think this process as isentropic process, so that the modulus of elasticity, isentropic modulus of elasticity is used, and this can be shown by the theory of physics is equal to A. What is that? A acoustic velocity, acoustic velocity or velocity of sound in the medium at that condition. This I told you earlier in relation to difference between incompressible and compressible flow. So this is equal to the velocity of the flowing medium to the velocity of sound, that is the acoustic velocity in the medium at that condition, and this ratio means the equality of Cauchy number or the magnitude ratio of Fe by Fi. This is proportional to this. That means one can tell that this ratio in terms of V by A, that is the velocity of the flow medium to the velocity of the sound in that medium at that condition. So this number is known as Mach number, which is conveniently used to represent the dynamic similarity for flow situations where elastic force is important, and known as Mach number, where Mach is the name of an Austrian physicist, that Mach number. Now we come to a very important query. Now we see that in practical problems, what we have concluded, that in practical problems, for dynamic similarity to be obtained, to obtain the dynamic similarity, we require that the ratios of forces, ratios of corresponding forces at similar points to be equal between the two systems at different operating conditions, and thus we arrive that a number of dimensionless terms arises. Now in a particular situations of fluid flow, sometimes it is difficult to find out from the force concept that the ratio of forces proportional to certain non-dimensional term, combination of the dimensionless variables, but it is easier to recognize the problem by their dimension, by its dimensional variables. Now there must be some easier way to find out what are these non-dimensional terms which govern the similarity criteria of the problem or which ultimately define the problem. Now let me put the question like that. If there is a problem defined by a number of variables, some m number of variables, so if that particular problem has to be made similar with a problem at different conditions, that means there are several same class of problem but under different set of conditions, then definitely certain dimensionless terms have to be kept fixed for both the problems, which represents the criteria of similarity, mainly the dynamic similarity. Now question is that how do you find what are such combined or such non-dimensional parameters which are the combinations of dimensional variables? It is not always easy to recognize the different forces governing that flow of fluid and their magnitude ratios. Number two, as we have already appreciated that in pipe flow problem, for example, that pressure drop is a function of so many parameters like velocity of flow, diameter of the pipe, density, viscosity, but we have finally recognized that this same problem can be described by two dimensionless parameter. One is friction factor and this is Reynolds number. So therefore the two things come into one. That means a problem can be made similar provided the dimensionless parameters, few dimensionless parameters are kept fixed for problems at different altered conditions of the same physics. And at the same time, this problem of a particular physics can be described by these dimensionless parameters, less number of parameters rather than the dimensional parameters. So now the question comes, how can we find out these dimensionless parameters? But for an example, let us just see this thing. Let us see that a pipe flow problem, we know that delta P is proportional to, depends upon what? Delta P depends upon the velocity of flow, depends upon the length of the pipe, depends upon, let this is length, depends upon the diameter of the pipe, depends upon the viscosity of the fluid, depends upon the density of the fluid. But at the same time we know that for similarity concepts, now from our previous knowledge, we know that friction factor becomes a function of Reynolds number only. What is friction factor? If we define friction factor is delta P dH by L rho V square. I am not doing away with the half thing. And this is a function of, okay, rho V d by mu. Now, from the concept of similarity, we will see that these two terms are the terms which define the dynamic similarity parameters. Dynamic similarity parameter is defined by rho V dH by mu as Reynolds number, then delta P by rho V square as the Euler number, and definitely L by D for the geometric similarity. But these three dimensionless parameters representing the dynamic similarity may be also clubbed in this form, so that the entire problem may be described as a parameter this is a function of parameter this. Let this parameter is x1 as a function of x2. Now question is that if it is so obtainable, then it is very fine. This is because if we feel that the only independent variable is this group, then we can vary any one of these and we can predict the variation of other parameters. For example, by varying V, we can cover a range of RE. For example, RE from 10 to 1000, we cover the range of RE. And we can predict the friction factor as a function of this RE by a single curve and by a limited number of experiments only varying V from 10 to 1000. But if this is possible to express the same phenomena by these two dimensionless parameters, that means that it is possible to predict the variation of other variables to the variation of V only, because a change in RE may be affected by change in any of the parameters. If I tell that RE is doubled 100 to 200, it may mean that it is doubled either by doubling velocity or by doubling density or by doubling diameter or by halving the viscosity. So it does not matter which one has been changed. That means by varying one parameter, it is simple to vary velocity of flow. We can cover a range of Reynolds number and we can predict the friction factor. From the similarity point of view, if a system prevails under two different conditions so that the range of Reynolds number is same, then the friction factor versus Reynolds number curve will be equally applied in both the cases. Only thing is that one has to read the friction factor from a given Reynolds number and accordingly he has to decode for his pressure value depending upon its value of diameter, its value of velocity, what is prevailing in his set of conditions. But the range of Reynolds number has to be made same so that we can make the dynamic similarity, and at the same time the L by ratio has to be same because the geometric similarity has to be maintained. So this is very simple and we understand this, but the question comes in such complicated problems, different problems, how do you know this combined dimensional variables as the dimensionless parameters which define the problem, which is other way explained by a number of dimensionless variables? That is very simply given by two mathematical theorem. One is due to Buckingham, that is the name of the scientist, another is due to Rayleigh, and these two theorems are known as Buckingham's theorem, another is Rayleigh's theorem. And these two theorems, the analytical theorems or analytical procedure, is based on one condition. That condition is the dimensional homogeneity of the physical variables involved in the problem. And how it is done, you see, the two problems, one is Buckingham problems and this is known as Buckingham's pi theorem. Why what pi comes? Buckingham's described this dimensionless term as pi theorem. What is this then? Buckingham's pi theorem is the most or the easiest method to develop the non-dimensional terms. Now our basic objective is like that. For example, if a problem, if any physical problem is described by m number of physical variables. For example, if you know pipe flow problem is described by pressure drop, length of the pipe, diameter of the pipe, density of the pipe, viscosity of the pipe. For example, a free jet problem is defined by the diameter of the jet, defined by the density of the jet, viscosity of the jet, surface tension between the jet and the ambient medium, the velocity of the jet. So we can definitely recognize, first this recognition comes from our brain, that from our understanding of the physical problem. No theorem beforehand will tell me, or no notebook will tell me, that open note examination, that no notebook will tell me that what are the variables that defines a particular problem. If we fail to recognize, very important here, that surface tension is one of the dominant variables which plays the role in case of flow of a free jet or flow of a liquid to a very small diameter in the order of 1 millimeter or less, that is our fault. So we will have to find out that what are the variables, physical variables that control the flow. So let us consider there are some m number of physical variables controlling or defining or describing a particular physical problem. Then analytically one can express the physical problem like that. That means if m number of physical variables like x1, x2, x3, these are viscosity, density, velocity, pressure, like that. If m number of physical variables are involved in describing a problem, then we can express the problem analytically like this. Function of x1 to xm is equal to 0 and by an implicit functional relation. Okay, m number of physical variables. Alright, now Buckingham told that if these m variables are expressed as n number of fundamental units, that if m variables are expressed as n number of fundamental units or fundamental dimensions, rather I write dimensions. What are fundamental dimensions? As you know, the fundamental dimensions are mass, length, time, temperature, current intensity or luminous intensity. These are the fundamental dimensions. In fluid flow, we are only involved with mass, length and time, not even the temperature. Please don't talk. Why you talk so much, I do not know. It is very shameful affair for IIT students. I am telling, so much you talk. Those you talk, you please go out. Don't create a disturbance. Others are also listening to this lecture. So they will know that IIT students are always talking like schoolboys. Even if their teacher tells like that, this is the scenario that happens. I am sorry to other listeners who are listening to this course that it is only meant for IIT students who are attending the course. In spite of telling so many times, they go on chit-chatting in the class. And probably this is the usual trend that you can see, that we will have to tell so many times you people at IIT that you please keep silence. And really I am sorry, and I have to be excused by other listeners that I have to do that, because simultaneously I have to conduct a class of IIT students who are continuously gossiping and having a chit chat in the class. In spite of telling so many times, I feel sorry to tell them and remind them again and again. But please be serious in the class. N is the number of fundamental units or dimension in which these m variables have to be expressed. If this is so, then Buckingham first proved that this physical problem may be described by dimensionless terms which he expressed as pi terms. These are the dimensionless terms by m minus n dimensionless terms. That means from m number of variables, the number of dimensionless terms is reduced to m minus n, where n is the number of fundamental dimensions in which the m variables can be expressed. And these pi terms are all the combinations of certain combinations. These may be x1, x2 by x3, x4, x1 into x4 by x1. So, these pi terms are the dimensionless term, that means certain combinations of the dimensional variables, and this has a physical meaning. All these dimensionless term represents the criteria of similarity. That means again I am telling that a physical problem which is described or defined by m physical dimensional variables is similar to the description, or you can tell can also be described in terms of m minus n non-dimensional variables instead of dimensional variables, by m minus n non-dimensional variables, where n is the fundamental dimensions in which the m variables can be expressed. So, therefore, we see we can recognize a less number of parameters, dimensionless parameters from the dimensional parameters to describe the same problem, and we have already recognized, or we have already seen the beauty of it through the pipe flow problem. Just an example I have given, that if we reduce the number of variables from dimensional form to non-dimensional form, that means we can vary one of the variables to vary the non-dimensional terms, any non-dimensional term, so that the effect of other variables defining the non-dimensional terms are clear or can be implemented. So, this is basically the Buckingham's pi theorem. So, first we learn the Buckingham pi theorem. Now, let us see that how Buckingham pi theorem is explained in case of a pipe flow. Laminar fully developed flow, laminar fully developed flow. Now, in case of a laminar fully developed pipe flow, it is true that we always consider the pressure drop per unit length. Why? Because length is not a pertinent operating parameter. Length of the pipe can change, and accordingly the pressure drop will change. And it has been found the pressure drop per unit length is the criteria, because in a laminar fully developed flow, pressure drop becomes a linear function of L. So, pressure drop per unit length is the output parameter which depends upon several input parameters or operating parameters of the problem. But what we think in this way, that a pipe flow problem is described or defined by what variables? First is pressure drop per unit length, another variable is velocity, another variable is pipe diameter, another variable is rho, another variable is mu. So, therefore, we see that these 1, 2, 3, 4, 5, these 5 variables define the pipe flow problem. There is no other variable. So, pipe flow problem is defined by its flow velocity, pressure drop per unit length, diameter, rho and mu. So, we can write that a pipe flow problem can be mathematically expressed by an implicit functional relationship of this. But what is the functional relationship explicit form? That is very difficult to know. Either one has to find out from experiments, or one has to make a theoretical analysis. Of course, laminar flow, the theoretical analysis comes from an exact solution, and one knows the Hagen-Poiseuille equation which exactly defines the relationship between these parameters. But in turbulent flow, one cannot do theory so easily. Turbulence models have to be employed, and they are dependent on experiment, so that one can find out from experiment that what are the functional relationship. In that case, what he has to find out, first of all he has to recognize that this is the output parameter. So, this is a function of all these input independent parameters. So, he has to vary this keeping all this constant, then influence of this on this. He has to vary this keeping other constant, influence of this on this. But without doing that, if we know that this phenomena can be reduced, that to describe the same phenomena, we can reduce the number of variables from so many to a lesser one in non-dimensional term, that is better. Now, we will apply Buckingham's pi theorem to that, how to find out the pi term. So, principle is like that, you consider first 3 variables out of the input parameter. First recognize which one is the output parameter, that is pressure drop per unit length. This is the predicted parameter to be predicted. So, out of these input parameters, you choose n number of repeating variables. What is meant by repeating variable is will be clear afterwards, just in the next step. So, n number of repeating variables to be chosen first, to be chosen. N number means n is the fundamental dimensions in which the variables have to be expressed. Now, here the variables are expressed in how many fundamental dimensions? All the variables are expressed in m, l and t. We require only 3 fundamental dimensions, not more than 3. Though in general physics the fundamental dimensions are more than that, but here in this problem we require only 3 fundamental dimensions, mass, length and time, to discuss the problem. So therefore 3 numbers of repeating variables we choose. Let us first choose V, dH and rho. Okay. Let us first choose the parameter V, dH and rho. Let us choose the V, dH and rho as the parameter. V, dH and rho. Now Buckingham told that now you can tell that any 3 we can choose. There may be 1, 2, 3, 4 combination, 4 parameters are there. So combination of 3 repeating variables is 4C3, that is 4 combinations are there. They are V, dH, rho. dH is the hydraulic diameter. V, dH mu, dH rho mu, V rho mu. So we can choose 1, 2, 3, 4. 4 choices there. Now there are certain rules for choosing the repeating variables. So repeating variables should be chosen from the input parameters, excluding the output parameters or performance parameter, and repeating variable should contain all the fundamental dimensions, not in a single one but collectively. That means if I choose V, dH, rho, all the fundamental dimensions are there. If I choose V, dH, mu, you see all the fundamental dimensions. Here probably in all the repeating variables choice, all the 3 fundamental dimensions are there. So we are little bit misled. Okay, let us see, I will explain, there is no misleading thing, but let us first try with V, dH, rho as the independent parameter. Now let us start with that the problem is defined by delta P by L V, dH, rho mu. So through a problem only I am defining. That means first step of Buckingham's pi theorem is choose any 3 repeating variables. Let us choose V, dH, rho as repeating variables. The rule is that these repeating variables should not include the performance parameter and should include all the fundamental dimensions. Then set the pi terms by raising the repeating variables to an unknown integer exponent, and any of the remaining parameters, that means V, dH, rho. So remaining parameters means one is delta P by L and another pi 2 will be V to the power A, another pi term will be, these ABCs are different, another remaining pi term mu. That means if there are x1, x2 to xm variables are there, if there are n number of fundamental dimensions, choose n as repeating variables. That means x1 to the power a, x2 to the power 2 a b, x3 to the power c dot 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 xn to the power n times the remaining variables, that means xn plus 1. Like that, x1 to the power, this is the general description, x3 to the power, that means first we choose x1, x2 to xn, some n variables as the repeating variables to the power n, x to xn plus 2. So this way we will be getting only m minus n number of terms, n plus 1, n plus 2 like xm. So there will be m minus n pi terms. That means you choose 3 variables, 3 fundamental dimensions, we choose any 3 as the repeating variables by the rule that it should exclude the performance parameter, it must contain the fundamental dimension. Then when I choose 3, here m is equal to 5. So 2 variables are left. So one pi term, that means these pi terms are this is known as pi terms. Pi terms, that means non-dimensional term, will be found out by raising these repeating variables to arbitrary unknown integer as index into multiplied by one of the remaining variables delta PL. Next pi term is another remaining variable. So here will be 2 pi terms because the Buckingham pi theorem tells that m minus n. So number of pi terms first is fixed. So number of pi terms is fixed according to Buckingham pi theorem. If m is the variables defining the problem, if n is the fundamental dimension in which it is expressed, so number of pi terms is m minus n. So in this case 5 minus 3. So 2 pi terms, it is already decided. How to find out 2 pi terms? That pi 1 is this, pi 2 is this. But we have to know the value of ABC to find out this pi 1 and pi 2 terms explicitly. This is done by equating the fundamental dimension. This is dimensionless term. Let us find out now. This very good. Pi 1 is v to the power a dh to the power b rho c delta p by L. What is pi 1? This dimension is m to the power 0 L to the, because dimensionless term. What is v? V is L t to the power minus 1 to the power a. What is dh? L to the power b. What is rho? M L to the power minus 3 to the power c. What is delta p by L? Please tell me. Delta p is m L to the power minus 1, L to the power minus 2, t to the power minus 1. Because delta p is what? P is m L to the power minus 1, t to the power minus 2. That is force by area. So divided by L, L to the power minus 2. T to the power? Very good. So you solve it, and what you will get if you solve it? M0. So what is the M? C plus 1 is equal to 0. C plus 1. L0, equate the exponents. What is L0? A plus B minus 3C minus 2 is equal to 0. T is 0, that is minus A minus 2 is equal to 0, which gives C is equal to minus 1. A is equal to minus 2. So minus 2 plus B, C is equal to minus 1 means plus 3, minus 2 is equal to 0. What is B? 3 minus 2, 1, 1 minus 2, B is equal to 1. So pi 1 will be V is equal to the power A is equal to minus 2, V to the power minus 2, dH 1, rho to the power C is minus 1, rho to the power minus 1, delta P by L. So this will be dH by L delta P by rho V square. You see, this is precisely the first pi term, which is the friction factor. So this is pi 1. Second pi 2, quick. Second pi 2 terms is V to the power A dH to the power B rho to the power C, and another term is mu. So M0 L0 T0 is equal to LT to the power minus 1 A dH L to the power B M L to the power minus 3. What is the dimension of mu? This you will have to know. M L to the power minus 1. This you will have to know, or you will have to derive. Where from you will derive the dimension of mu? Tau is equal to mu du dy. You know the dimension of stress. You know the dimensions of u, you don't know dimensions of y. This is done at school level, I know. So now you cannot tell me that I know that this dimension of mu is done at school level, m L to the power minus 1, t to the power minus 1. If you do that and solve it by equating the exponent, you will get A is equal to B is equal to C is equal to minus 1. So pi 2 is mu by V dH rho. So therefore the problem is described by pi 1, pi 2, 0. So this becomes is equal to delta P by rho V square into dH by L and mu by V dH rho as 0. So this is pi 1 and this is pi 2. If you make this reciprocal, then we get that this is delta P rho V square dH by L. Reciprocal of this, that means if it is governed by this parameter, it does not mean it is same that it is governed by the reciprocal. If y is a function of x, means y is a function of 1 by x also, because this is the conventional Reynolds number. So therefore this is friction factor F is equal to 0. So this can be expressed as friction factor is a function of RE. That means function of pi 1, pi 2, 0 means pi 1 is a function of pi 2. Pi 1 is a function of pi 2. That means friction factor is a function of RE. Alright, so friction factor is, that means we get the relationship. Therefore we say that this problem is defined by these two function, this pertinent dimensionless terms. So, now after this I like to tell you that the very important thing that we have several other choices for the repeating variables. So, this choice gives these two parameters pi 1 and pi 2 like that, delta p rho v square dhl and pi 2 as mu by rho v dh. But what are the pi terms we landed up with if we choose these three sets as the repeating variables? That I will discuss in the next class. So, at the end today I just tell you that while discussing at the beginning, which is very important, that pertinent dimensionless terms which have come, the representative magnitude of forces, you must remember this, rho L V by mu is the inertia force by viscous force, that is Reynolds number. In fact, everywhere inertia force comes at the denominator, but here inertia force is numerator, but there is no such convention. Sometimes in some problems the reverse of this or the reciprocal of this is defined as Froude number. Surface tension inertia force, the elastic force, inertia force by elastic force, this is the Mach number, this is the definition. Of course, the inertia force is at the numerator. This is because that all these numbers were not originated first from the principle of similarity. It came just from the intuition by doing an experiment. While Reynolds first started doing an experiment with the pipe flow in a laminar region by seeing that how the flow transition takes place from a particular one to another type, that means laminar to turbulent. He first found out the combination as the pertinent governing parameter. So, this was named after his name as Reynolds number. Ultimately, from principle of similarity, his intuition was there that probably this combination physically signifies something, and the principle of similarity came out. So, it was inertia force by viscous force. Sometimes the Mach number, inertia force by elastic force, but somewhere there the Euler number is pressure force by inertia force. So, these are the conventional form where these numbers are defined, and they are the representative magnitudes of certain forces as the criteria of dynamic similarity. It is very important. Okay, thank you.